Robot localization in a pool. We consider an underwater robot moving in a rectangular pool. The length and the width are known, and there is a sonar in the center of the robot which rotates. And the angle of the sonar is delta. The depth of the robot can be obtained by a barometer, which is assumed to be known perfectly. The robot is such that the bank and elevation angle are both equal to 0. It means that the robot is able to move horizontally. So we assume that since the barometers has a good accuracy, the robot moves in a plane at a constant depth. So the problem we have is to localize the robot, so to find x and y, using the sonar angle delta. So this is here our robot. We can see that the sonar has a direction given by delta, the angle with respect to the head of the robot. So the heading is theta. The location of the center is x and y. So what we need to find is x and y, and also we'll try to obtain the speed v. So we assume that theta is known thanks to a compass, and the angle delta is also perfectly known. So the aperture angle of the sonar is p divided by 4, so on the left and on the right. It means that the sonar illuminates this sector here and is not able to see what is in the dark blue area. So the sonar will return the impact point, so here, the hit point, it will be here. So why? Because there is some specular reflection here, which means that the sound moves like this, but here it will rebound and will not be measured by the sonar itself. So only this distance will be obtained by the sonar. So why it is important to find x and y? We'll illustrate on a video. This is our robot which is moving inside the pool, the rectangular pool. So it knows its depth, so it is able to go to the horizontal plane in order to accomplish a mission. So the sonar, which is below the robot, is able to measure distances to the walls, and from this it will be able to go from one point to another in the pool. So this is here the robot Exercice from Bretagne, which participates to the Exercice competition. The robot is totally autonomous. The tangential acceleration A is measured with an accelerometer and corresponds to the main propeller. Every dt equal 0.1 second, the sonar sends a ping, ultrasonic ping, and returns the distance to one of the walls. So we need to know which wall it is. And the wall which is impacted is called the hit wall, and it has a number equal to W. So W, the number of the wall, only depends on the head of the sum theta plus delta, where theta is the head of the robot and delta the orientation of the sonar. So I will explain here. So in this picture, for this configuration A, the sonar points in this direction, and in the configuration B, the sonar points in this direction. So in this case, the sonar will not return this point, but will return this point. So it will measure the distance to the wall 1. This is why W, the hit wall, will correspond to 1. So we have 4 walls up from 0, 1, 2, 3. In this configuration B, the sonar is oriented on the left of the robot and will return this impact point. So the hit wall will correspond to W equal to 2. If I take this robot, for instance, and if I move it in this direction, then the impacted wall will remain the same. So the hit wall will not depend on the position of the robot, but just on its orientation. So it will depend on theta plus delta, but not on x and y. W depend on this. And recall that we measure this one thanks to the compass, and we measure this one since it is the angle of the sonar. I have here a diagram which tells me that if the sonar has this direction, or this one, then the impacted wall, the hit wall, will be the wall number 1. And we can see that here this orientation corresponds to this one in the diagram, and this one corresponds to this one in the diagram. This is why the hit wall for configuration B is the wall number 2. In this exercise, we want to build a Kalman filter which estimates the position x and y from some measurements. So the measurement will be A, the acceleration of the robot, L, the distance to one of the wall, theta, the heading, delta, the angle of the sonar. And for this, the Kalman filter needs to imagine a linear world. So I will have to create some linear equation which correspond to the situation where the robot is moving inside the pool. Question number 1. The Kalman filter assumes some linear state equation where the input is A and the output is named here Rk, and I will have to find it. And I have to give the expression for A, B, and C, so that the Kalman filter will give me some estimation of x, y, and v. I have also to explain what is exactly R of k. So I assume the kinematic equation given here. So it means that the derivative of x and y depends on the speed v and the heading theta, and the derivative of v is the acceleration a. So if I take this equation, and if I say that z, the state equation inside my Kalman filter, is corresponds to x, y, and v, since I have to estimate them, then I will have from this equation z of k plus 1 equal, so I will have here the identity a1, 1, 1, 0, and here cos theta dt, sine theta dt, here 0, 0, 0 z of k, plus 0, 0, 1 dt, times the input a of k. So the reason for this, let me take for instance the first equation. The first equation tells me that x of k plus 1, so the first because of this, is equal to 1 times z, so 1 x of k, plus cos theta k dt, due to this, multiplied by the third component of z, it's v. So this is a Euler discretization of this first equation, and this is the Euler integration scheme of these three equations. Here I have my matrix A of k, which is this one, and this is B of k. Now I need to have C of k for the observation equation. So for this I need to know which is the heat wall. The heat wall is given by the following formula. I will explain it after. It is the modulo of something n4, because I have 4 walls. And here I take the round, so the integer which is the nearest, multiply by of 2 divided by pi, multiply by theta plus delta. So let me explain this. So here multiply. So it's important to have an integer which is always between 0 for wall 0 and 3. This is the role of the modulo. This is to have an integer. Now I check that if I take this one and if I add to this angle p divided by 2, then it means that the sonar rotates by p divided by 2, and of course the wall will increase by 1, which will be the case, because 2 divided by pi multiplied by pi divided by 2 will be equal to 1. Since I have also to check that for theta plus delta equals 0, then the round will be 0, the modulo will be 0. It means that when the sonar is in this direction, then W will be equal to 0. Okay. Now I need to check what is the matrix CK. So for this, I will consider different situation. First, if W equal to 0, then I will consider W equal to 1, then the situation where the heat wall is 2, and here the heat wall is 3. So in this situation, I will have here the distance I will measure if the heat wall is 0 will be this one, and it corresponds to L. L will be equal to Rx minus X. This relation can be rewritten as Rx minus L equal to 1, 0, 0 multiplied by X, Y, and V. So this is Z. This is CK, and this is RK. So it means that in this situation, I will have RK equal Rx minus L. This CK will be equal to the matrix 1, 0, 0. So now, if W is equal to 1, then I will have the relation L equal, so it will be Ry which will be involved, so it's Ry minus Y, and in this situation I will have here Ry minus L, and since Y is involved I will have 0, 1, 0. Here I will have L minus Rx, here L minus Ry, here I will have L minus Rx, here L minus Ry, and again 1, 0, 0, 0, 1, 0. Question number 2, I will simulate the robot in the pool, and the motion will be described by the state equation given here, with 3 inputs u1, u2, u3, and 5 state variables x, y, theta, v, and delta. We'll assume that the initial state vector is given here, and the input is constant and given by the vector u. Then I will have to use the Kalman filter to localize the robot. And to avoid outliers, I will only consider the distance when the sonar beam is orthogonal to one of the walls. So I am sure that the impact point will correspond to one of the wall without any ambiguity. So for this, I will consider the following program for the simulation, and the evolution, the state equation given here involve a state equation, the evolution function f, which depends on x and u, and which is given here. So I extract x, y, theta, v, and delta from the list built from x, the state vector, and the same for u, and I return this, which corresponds to the evolution function. Here I draw the robot, but I will also draw the beam, this vector, which gives me the direction of the sonar. When I will draw the simulation, I will draw also the polygon which correspond to the pool, and also I will draw the robot thanks to this function given here. I initialize here the length and the width of the pool. Here my TT, and then I will simulate the evolution of the robot thanks to an Euler formula. Here I will initialize my state vector as asked in the exercise, and u here is chosen here. I have this program, I run it, and I can see here my sonar turning around the robot. My robot has to know which wall is hit. This is why I have to compute W. Here the modulo is given in Python by this symbol. Then I will, to be sure that I do not make any mistake in my program, I will draw the hit wall. So it will be this wall here. And I will do it by extracting from the polygon which corresponds to the pool, so P like pool. I will extract, so I will compute K, which corresponds to my wall, and then I will draw the segment corresponding to this wall. And again, I will simulate my robot by taking U1, U2, U3 as here. It means that U1 is equal to 0.2. It means that my robot will turn slowly on the left. Since V equal to V dot equal to 0, it means that my robot will have a constant speed. So A will be equal to 0 because A will correspond to U2, 0. And the last one corresponds to the speed, the rotation rate of my sonar. It means that it turns quite fast. I take my program, I run it, and I can see here the wall, red, red, and we can see that it corresponds to the direction of my sonar beam. The simulator not only needs to know which wall will be hit by the sonar, but also needs to know this distance, delta, which is the distance between the robot and the hit wall. So from this we have our polygon. So the polygon is given here, is made with point. The first point is this one, the second one this one, third, fourth, and I come back here. This is why here I have 4 points where X, Rx, and Ry are involved. So to compute the distance which corresponds to a function of X, the observation function, plus a noise, here, a Gaussian noise, I need to build a function J, given here. From this, I extract my state variable, I compute the heat wall, then U correspond to the sonar beam. I extract A and B. In my situation, A, B are here because it corresponds to the heat wall. Then I return the distance, and also since it is my observation function, all I measure in my robot, I also have not only the distance L, but also theta, the heading, and the angle of the sonar. So if I do this, I will draw my beam. This is why I will see now the segment which goes up to the heat wall in my simulation. So this is why what I will show now. I do this. I have here the distance which is returned, and we see that the distance is not always the length of the beam, but always corresponds to the distance between the robot and the heat wall. To implement my Kalman filter, I will first implement the prediction part. So I will consider that the Kalman filter first as a predictor. So it means that I do not take this equation into account first, and then it means that I don't have this information, only the prediction part. So for this, I recall that AK and BK are given by this, and this is why I implement AK here and BK here in my predictor, so which is named here localize. So at each step I will localize, and my Kalman filter will return the prediction for Z corresponding to X, Y, and V, and will return also the covariance matrix. I will draw here the corresponding confidence ellipsoid. Here I call the Kalman filter as a predictor. if I do this, I will obtain here this localization. So first, my initial condition is well known. The distance is not taken into account. So the robot blindly is able to have an estimation of its position, but also on its speed. We see that the confidence ellipse increases. Now I will implement the observation step in my Kalman filter. It means that I will consider the observation equation. So for this, I will now consider that I don't know my initial position and my initial speed. It's why I put for z hat 0, 0 and 0 for the speed. And here I put a large covariance matrix just to say that I have no idea where is z hat. I can put larger, of course, but I know here the dimension of the pool and I have a poor idea of my speed. Then here I will localize, but now I will initialize the wall, the heat wall, to 0 because I don't know where is my initial heat wall. Okay, for the localization now I will have u and y as an input, my heat wall, and the approximation of my state. Then I will compute the heat wall here, and I will consider the measurement for correction only in the specific situation where my sonar direction is perpendicular to one of the wall. So it means that this angle theta plus delta should be something like kp divided by 2. This is given by this condition. Okay. But also I consider only the situation where I change my wall. Okay. So it means that when my sonar will turn by p divided by 2, then I will have new heat wall, so I will consider a new measurement for my correction. Depending on the wall, 1, 0 up to 3, I will take the right RK and CK for my observation equation. So these values give me this one here in my program. Then I will call the correction step of my Kalman filter in order to improve my state and decrease the corresponding covariance matrix. Then I will draw magenta, the covariance matrix, and blue when I have the prediction. And I will wait a little just to see this magenta matrix. And I will draw the estimation in yellow to see the difference between the true robot, which will be black, and the estimation, which will be yellow. And of course, the prediction step is called more often than the correction step due to the fact that I want to avoid outliers and I only consider a situation where my sonar is orthogonal to the wall. I take the program, I will simulate it, and I have my initial localization, which was quite bad. I see the estimation in yellow, which is quite good.